I've been doing using the technique called Cornell force microscopy to image the spatial structure of moiré heterostructures. And just to give a brief and quick overview of moiré heterostructures, probably will not do it justice. Is that let's imagine I have in this case, a honeycomb lattice, and in this case, there are two layers. You can't see the other layers, but I rotate one layer with respect to each other. And what you see is that as you rotate the layers with respect to each other, you begin to see the formation of a lattice with a longer wavelength periodicity compared to the atomic lattice, which is known as the moiré superlattice. And this is what I'm saying, that twisting two layers with similar lattice constants will produce a moiré superlattice. But the important thing is that this superlattice creates a new periodic potential for the electrons, which modifies the state that they can occupy. And from the perspective of electronic band structure, in this case, I'm showing calculations from a thesis from a former group member of mine showing the band structure for different twistings for twisted bilayer graphene. And I guess the only thing I want you to focus on is that these bands in the middle, their width decreases for certain angles. And this behavior was predicted by Vishwasthar and McDonald in 2011 for twisted bilayer graphene, in which they found that at a particular magic angle, 1.1 degrees, the graphene layers, you get a flat band. And this is interesting because electrons in a flat band have reduced kinetic energy, and the group velocity of electrons is proportional to the slope of the band. So that's why the kinetic energy reduces. But this means that the interactions between electrons dominate the system. You could perhaps see some interesting behavior. And so in 2018, when the first generation of devices came from Pablo Rodriguez group at MIT, they found that indeed in this case, they have something of 1.16 degrees, that they found that they had superconducting states as well as what they call a Mach or correlated insulating state. But quickly after, Aaron Sharp in my group found that there was actually in the twisted bilayer system also paramagnetism. And then shortly after that, Andrea Young's group at Santa Barbara found that actually this magnetism is actually, there's a topological Chern phase in which they saw the quantized anomalous Hall effect, the quantum anomalous Hall effect. Quantum anomalous Hall effect is the zero field analog of the quantum Hall effect. Sorry, I'm speeding through this. But I guess the interesting thing is that the flattening of bands can produce interesting electronic properties. And I guess, so what I've shown so far has just been for twisted bilayer graphene, but since then, people have extended these systems beyond graphene systems. You'll hear from Kim Fai Mak about using transition-level dihalogen to observe some interesting physics. But one thing I'd like to take a step back and focus on is that what is this twist angle that they report from their measurements? And how is that actually related to the spatial structure of the moiré? And so I won't go into the details, but using transport, we can extract information about the average moiré unit, so you can figure out how many electrons you fit into the system before you reach the band insulating state. And just from that area, you can extract the twist angle, because you know how the length for the area of the moiré unit cell scales. But this twist angle is determined by just measuring voltage and currents. They don't really reveal any information about the spatial structure of the sample. And in particular, what this means is that the relation between the actual spatial structure of the moiré and the measured electronic properties has been relatively unexplored thus far, since the field of moiré started in around 2018. In particular, I think we still don't know what electronic properties a very disordered moiré can show. And so, as well as how could these properties differ from what is measured in a more uniform array. But I say more uniform just for the example, but if you look at the scale, this is a 2 micron image, this is a 200 nanometer scale image, but this is just the motivated idea. And what I hope to achieve is that by imaging the moiré spatial structure and imaging the spatial structure of the moiré could provide complementary information to information we obtain for electronic transport. And using the combination, you could hopefully begin to understand new things about these systems. And so I guess I started showing you these images. These are images that Mihir and I acquired over the last year. So I'll just now quickly go back to the concept of cortical force microscopy for imaging. And so this image is adapted from this paper that we was recently accepted in the National Academy of Science. And the basic idea is that we have a cantilever in which we shine a laser off and measure the reflection of this laser on some photodetector. And the key idea here now is that we excite mechanically a torsional resonance in the cantilever. And so what this means is that the cantilever will bend back and forth. This will produce a signal on the lateral signal on the photodetector, who's oscillating at the frequency of our resonance. But I guess if you're interested, you can read more about the paper. But the idea is that this technique is very sensitive to friction, and so we can look at the dampening or in our amplitude of our signal as we scan across the sample. And in particular, you would expect these different regions where the atoms of the two layers are stacked on top of each other, the so-called AA stacking, produce a different frictional response than the AB stacking. And so what is this technique capable of measuring? We can, as I showed, we can image a single moiré superlattice. But if you're lucky, if you can also measure simultaneously two supermoiré lattices, that is available. And the reason we found that we can actually observe the atomic lattice of hexagonal boron nitride as well as graphene. And so we can extract a lot of information about the physical structure of the material of the samples. Okay. So now what I'd like to quickly shift gears is extracting quantitative information about like the wavelength and periodicity of these structures. And just, in practice, this is actually a little bit tricky just because of the nature of the technique. The images that we acquire from this technique are very distorted due to various mechanisms. But the two common sources of distortions are non-ideal behavior in the motion stages, as well as thermal drift between this probe and the cantilever, or probe and the sample, sorry. And so here is just a quick example. So here I'm showing the same scan. On the left is what I had intended the tool to do. So I had intended to scan originally a 7-nanometer scan. But actually, if you look at the encoder readout, which just tells you basically how much the tip moved, actually, you see that it actually didn't measure the scan area that I measured, or that I wanted to. And this has implications for our assignment of distance because if we had not used the encoder readout, our estimation of the length of pixels would have been incorrect. And so how can we extract the spatial information or periodicity from these images? The simplest thing is to use a 2D Fourier transform and look at the Fourier peaks. And by using the magnitude of the Fourier peaks, we can back calculate the wavelengths of the moiré. You could, in principle, also apply just looking at the real space image, apply in a signal to noise that you could just try to extract this real space image. But so what this means is that so if you did not correct for the encoder readout, you would see that the positions of the Fourier position peaks would have been in different locations, and this has implications for our extractions of the wavelength. And so now I do the back calculation of the wavelength using the Fourier positions shown on the right. You can see that our wavelengths would have been off by around 15 to 20%. And what this means, if you assume strain in your system and try to determine the twist angle from that, you would have underestimated your twist angle by about 0.23 degrees, which is dramatic in terms of the band structure. And so this is just one case analyzing a single image. In principle, we'd like to add in some type of error bar to our measurement. And so what you can do is that you can measure the same region repeatedly. And so what I'm showing in this plot, these arrows denote the scan directions which go in the same direction. So to acquire this image, we scan from left to right. So we build vertical lines left to right or right to left. And what you see is that at least the one calling this 60-degree peak is that if I'm tracking the position of this middle peak, the 60-degree peak, and just showing what the wavelength is. And what the interesting thing is, okay, if you just track this peak over multiple scans, you see that there's not much of a spread in the extracted wavelength. But if you go to a slightly different peak, you see that, okay, it does slightly worse. There's actually, it looks like forward and backward asymmetry to the assignment of wavelength. And so this is a little bit problematic, but we believe that this forward back asymmetry is due to the other component that I have yet to mention, the relative drift between the sample and the probe. So just for reference, even number scans go in one direction, odd scans go in the other direction. And if I just quickly flash back and forth, you'll see that the two scans are slightly different from each other. And so that's why we saw that forward back asymmetry. So just to, I guess, provide a little bit more supporting evidence that there is a relative, if you compare scans that all go in the same direction, you'll see that the sample is actually slowly marching up. And this is why we believe there is a thermal or a drift in the system. And so moving forward, we're hoping to work on a protocol to undistort the images. So take into account this thermal drift to get more at the ground truth of the structure. And then also, we hope to soon begin mapping structures on device relevant length scales like the microns and characterize the twist angle and strain, and hopefully place electrical devices in the same region, and so we can begin to correlate this physical spatial structure to the measured electronic properties. And with that, I'd like to thank Mihir Kandakar, Gregory Zaworski Jr., and Joe Finney, who we put a lot of work into the initial stages working on TFM and trying to find applications or finding out what makes it work. This work was also done in close collaboration with Professor Annie Manners, the Material Science Department, and as well as Bede Pittenger at Bruker, who provided a lot of insight on the hardware of the tool. And then also my group, Christina of the shared facilities, and then this work was funded by BOE through SLAB. Thanks.
We don't do questions, so we'll now. No.
So I gather that the end of the talk is enforced very vigorously here, so I'll keep my introduction extremely short. It's wonderful to have Fai Mak here. I did what you always do when you're getting ready to introduce somebody. I looked up his publications on Google Scholar, and it's just astonishing how many papers with thousands and thousands of references he has. So I won't try to summarize this, but what I will say, since maybe there's a somewhat broader community here, there's been really quite a revolution in the study of this matter physics point of view in study of quantum materials that has been opened up by various ways of engineering interesting electronic structure in van der Waals materials assembled in one intentional way, another. And one of the great leaders in this area has been Professor Mak. In particular, there's been enormous interest in properties of transition metal dichalcogenides, or to say that, which are both semiconductors and have interest in strong correlation and spin orbit coupling effects. And this has opened up astonishingly rich new areas of physics that many of us here have been trying to understand based on the field that's been open. So anyway, it's really a great pleasure to have him here today. Oh yeah, and he was a student of Heinz, not at Stanford, but okay, we've been playing partial.
Thank you very much for the kind introduction, and it's been wonderful to visit here and interact with colleagues in our field and also outside of our field. And I actually feel the pressure of speaking here, particularly in front of my PhD advisor. With that, he's actually very considerate. He decided to move back to his office. Okay, then I feel less pressure. Okay, so today I'll be talking about a particular type of electron fractionalization realized under zero magnetic field. And but before that, let me just really acknowledge the people. Chern, we share that at Cornell. The first part of the talk, we're talking about fractional Chern insulator. The two, main people who are responsible for the work in Yang Zheng and Chern Xia. And the second part of the talk, we're talking about fractional topological insulator. I hope that will be able to convince you that the work was really, really led by talented student Kai Pei Kang, and also by Warren Shen and undergraduate student Yi Chun Chiu. And boron nitride crystals that we use are from Japanese groups. But a very general introduction in electron fractionalization. There are two types that I know, which is pointed out in this reference here by T. The first type is spin charge separation. We have to split the electron into a spin carrying part, the spin arm carries a spin but no charge in the fermion. And then the charge part, which carries the electron charge but no spin, the charge on which the boson here. And it's expected to occur in 1D electron liquid, quantum spin liquids, probably no experimental realization yet, and also probably near some quantum critical points. The second type of electron fractionalization is really just split the charge of the electron into fractions. And that's really realized, in the famous example of fractional quantum vortex. And in this kind of phase of matter, it supports dot excitations, which are vortex-like, but with that support the fractional charge. And today I'll be really just talking about this under the zero magnetic field. So the story begins, a more general introduction. The story begins with the observation of the quantum Hall effect. When you have a two-dimensional electron gas subject to a very high out-of-plane magnetic field, you form the Landau levels here. And if you happen to put the Fermi energy in between these Landau levels, you get a very nice quantized fold in measurement. And it's actually very accurate on precision accuracy. Half a billion now, even better than that. Yeah. And that was first discovered by So this robust quantization really highlights topological fraction in physics. Okay, something even more dramatic happened just 2 years later. Better sample, lower temperature, higher magnetic field. Stormer, and Gauss actually observed the fractional quantum Hall effect that not only takes an integer value of E square over a fraction of E square over H for the Rxy. And very soon, and Larkin actually came up with a many-body wave function, the famous many-body wave function, and really highlights the importance of the Coulomb interaction when you partially fill the Landau level energy gap can still be open. And that really just captures the effective sensitivity for the fractional quantum Hall. And but very soon after that, and it's a legitimate question to ask, can you observe the quantum Hall effect under zero magnetic field? And before getting into that, let me just quickly remind you of graphene. This is the honeycomb lattice structure of graphene. A and B sublattice sides both covered by carbon atoms. And because there's an emergent symmetry, you have a Dirac cone that supports electrons at the K and K prime points of the zone corners of the brilliant zone. Okay. And in 1988, Haldane actually came up with this model that, in addition to taking into account the nearest neighbor hopping, it considered the imaginary next nearest neighbor hopping, which actually is high phase shift for the hopping A site and the B site. So in this kind of hopping, basically, you can tell the difference between the two sublattices, and as a result, you can open up an energy gap at the Dirac point. But it opens up a gap in a very interesting way that it opens up a positive gap in this valley and a negative gap in the other valley, so that each of this valley contributes well over 2 H-Hall conductors, and when you sum them up, it becomes a Chern insulator that can exhibit the quantized anomalous Hall effect under zero magnetic field. So that was the first theoretical model. And so I think the concept can be generalized further that instead of putting an electron gas under a very high magnetic field, you could actually achieve so-called flat Chern bands. The bands look similar to the now levels through some kind of lattice model. If you build a lattice model for complex hopping correctly, and you can get this kind of flat Chern bands that can mimic the now levels with zero magnetic field. And if you build integer between this, the field between these two flat Chern bands, you get the quantum anomalous Hall effect I mentioned. And if you fractionally field one of these flat Chern bands, you may be able to stabilize a fractional Chern insulator that was first pointed out in 2000. And experimental progress of quantum anomalous Hall effect first observed in this science paper in 2013 in magnetically doped PIs. Then it's also observed later on in intrinsic magnetic PIs, not just disordered doped PIs, but its intrinsic structure. And later on, it's also observed in the graphene moiré lattices, out in the Cornell group and also in Andre Young's group in 2019, and also in moiré semiconductors in 2021. And these are actually examples from filling the flat Chern bands that I was talking about. For fractional Chern insulators, there was some claims of observing it, and first by Andre Young's group in this science paper in 2018. That's really like it's not really the same as this kind of a zero magnetic field flat Chern band picture, but it's really under very high magnetic field. You form this magnetic block bands, and you partially fill the magnetic block bands you observe. They also call it a fractional Chern insulator. And later on in Amir Kogi's group, they observed interested magnetic graphene not under zero magnetic field, but you apply a small magnetic field that can further flatten the band, and that also seems to also observe a fractional Chern insulator. And in both of these cases, magnetic field is required. In this case, it's about 5 Tesla. In this case, it's about 20, 30 Tesla. So I think in 2023, last year, there was the first observation of FCIs as zero magnetic field, and that's the first part of the story today. So let me then tell you about materials that we use to realize these phases. moiré semiconductors. This is the constituent. This is the building block material on the layer of EMD semiconductor. If you look from top down, it has a honeycomb lattice structure like graphene, except that the two sublattice sites are now occupied by different atoms. And electronic states of interest are also located at the corners of the brilliant zone. And because of the broken emergence symmetry, energy gap is open at the K and K prime point, so it's like gap graphene. It also has large spin orbit coupling that locks the spin to the outer plane axis. So actually, it's like effective Ising spin, or you can think of it as SZ conservation. SZ is a good quantum number. And so the electrons at K and K prime, they are sort of like breaking time reversal symmetry, but they break time reversal symmetry in the opposite way. So the overall system maintains the time reversal symmetry. And the spin states, for instance, at the K point here will be split into a down up, at the K prime point will split into up down. Okay, and the SZ conservation actually is important. And you can build moiré superlattices, just like what the previous talk about. And there are two ways to do it in this type of material. One is to use the same material, 2 layers, same material, we call it homobile layers, and you give it a twist angle theta, then you get a interference pattern like this. And the moiré period is about 10 nanometers, depending on twist angle. So the moiré period is about the lattice constant divided by the twist angle with a small twist angle. Or you can use heterobilayers. that we put two different layers, exactly match with the twist angle, no twist angle here. But there is a lattice mismatch, small lattice mismatch between these two materials. Then the moiré period is given by A divided by delta, and delta is the lattice mismatch. And that also gives a moiré period about 10 nanometer-ish, 5 to 10 nanometer-ish. Okay. And you can directly see the moiré lattices in collaboration with Dave Mueller's group at Cornell. This is looking using an STEM to look at the structure here, moiré stacked on top of tungsten selenide, perfectly angle matched. And in addition to the small dots, those are the real atoms. We can also see the interference pattern that produce the moiré structure. In this case, the moiré period is about 5 nanometer, and that's the inner cell of the moiré structure. Yeah, it's a hetero bilayer, so it's actually a little bit less disordered compared to the homo bilayer system. Okay, flat bands. Usually we are dealing with moiré materials in this limit, that the moiré period is much larger than the atomic length scale. So that to a very good approximation, we can even forget about the original lattice and just treat our electron with a certain band mass moving in the smooth periodic potential defined by the moiré lattice. And then you start with bands in the big Brillouin zone, get extra bright reflection due to the superlattice, you get a mini Brillouin zone, and a series of flat bands formed in this type of structure. So it's very simple. And in heterobilayers, if you don't apply any electric field perpendicular to the heterobilayer, the bands are typically, you have flat bands in both of the layers. For instance, in this case, with moly-telluride flat bands and tungsten selenide flat bands. The flat bands in both of the layers are very far apart from each other because of the work function mismatch in the two materials. And so to a pretty good approximation, in this case, you can think of that with my Fermi energy splitting one of the bands here. It has a pretty well isolated flat band. And the low energy physics actually has been mapped by Alan McDonald's group 2 years back. So that the low energy physics can be mapped to a Hubble model on a triangular lattice. That there is a tunneling, nearest neighbor tunneling for electrons occupying the surfaces of the triangular lattice. And if you happen to put two electrons on the same site, there's a large on-cyclone repulsion field. To give you a sense of the energy scale, the kinetic energy of the electron T is about 1 to 10 milli-electron volts in this type of system. The on-cyclone repulsion is about 100 milli-electron volts. So a system is strongly correlated with the Coulomb energy, usually dominant over the kinetic energy of the electrons. So that's under zero electric field that you have the bands from the two layers really far apart from each other. Now you can imagine if I apply a really large electric field, that I could in principle bring the two bands from different two layers very close to each other, and we can actually even band immersion, invert bands from the two layers. In this case, after the band immersion, you could get Chern bands in the system. Spin polarized Chern bands with finite Chern numbers after you integrate very curvature over the occupied states. And furthermore, actually has been shown again by McDonald in 2019 that this two orbital system actually in the low energy limit forms a famous K-Malay model that you can think of it that the orbital from the moly forms a triangular lattice, orbitals from the tungsten forms another triangular lattice, but 180-degree rotated. So overall, they form a honeycomb lattice. The nearest neighbor hopping here is the interlayer hopping between the two layers, and the next nearest neighbor hopping is actually intralayer hopping, which plays the role of the spin-orbit interaction. And furthermore, the sublattice potential here, which is represented by this last term here, is tunable by the electric field. So basically, the Stark effect that you apply the electric field perpendicular to the layer that continuously tune the sublattice potential in this Hamiltonian. And so that's why it's actually the Hamiltonian very tunable. You can change the system from topological trivial bands to some topological bands. And so now we actually really have a platform of flat Chern bands. And so it's really interesting to study interaction with different Chern insulators with this kind of system. And so it's actually, this kind of concept is not crazy, and it has been realized. First, in a bilayer system of moly-telluride tungsten selenide. For instance, we built the system at filling factor equal to 2, meaning that we fit 2 electrons per moiré unit cell in the system. That corresponds to putting the Fermi energy located between the two bands, one from the moly layer, one from the tungsten layer. That's before band inversion. So you actually have a trivial band insulator and filling factor due to the two. And you can apply electric field cause a band inversion, then you develop Chern bands, and supposedly you can get a 2D TI in this case. And in fact, experimentally, you can measure it. This is the dependence of the resistance of as a function of the electric field that causes the band inversion, a fixed filling factor equal to 2. And you can actually see that before the band inversion, the resistivity diverges in the low temperature limit, just typically for a band insulator. And after band inversion, in the low temperature limit, the resistivity saturates to a plateau with the electric field, and the value is pretty close to h over 2e squared. That's really supporting the emergence of the 2DTI state after band inversion. And if you, that's for filling factor equal to 2, and if you look at filling factor equal to 1, meaning 1 deduction from moiré unit cell, that corresponds to a half-filled moiré orbital here, a moiré band here. Before band inversion, the interaction will actually drive the system to a topological trivial Mach insulator, and after band immersion, the band is a Chern band, and the system actually would spontaneously break the values degeneracy of the system and drive it into a Chern insulator. And experimentally, you can see the quantized anomalous Hall effect under zero magnetic field accompanied by a vanishing news. So all these things actually can be engineered in this kind of moiré material. In addition to the heterobilayer I told you about, there is also the homobilayer. The physics that's actually very similar to the heterobilayer, except that at zero electric field, the bands are already inverted because the two layers they hybridize, and you already start with the Chern bands. And in fact, you actually have to apply an electric field in the homobilayer and invert the band to make the band be topological. Otherwise, the physics is just very similar between the heterobilayer and homobilayer. And this is kind of phase diagram. I will come back to it. And this is the electric field and the filling factor, which can be independently tuned in our devices. And typically for the homobilayer case, the zero electric field here is centered here, and the system is actually in the layer hybridized limit in the small electric field regions. And there, the bands are hybridized or inverted, and the Chern number for the band is not zero. And if you apply a large enough electric field, you actually can layer polarize the system, or you can think of it that I put a large enough lattice potential in the system. The bands become topologically polar, and no Chern number here is in the layer polarized regime. So this is a kind of a phase diagram here. So we have small electric field layer, Chern band, large electric field, no Chern bands. And the difference between homobilayer and heterobilayer is just that this electric field is centered at zero for homobilayer, but centered at a very large value for heterobilayer. Other than that, they are pretty similar to each other. Okay, so with this introduction, I will just tell you a bit about two topics. First is fractional Chern insulator, that's spontaneous time inverse symmetry, and the other is a demonstrated there we offer the time inversal symmetric fractional TR in the system, in this type of system. So first, let me just say that last year was a good year for FCI. First, it was optical signatures and thermodynamics interest of the FCI, and then just a few months later, there were direct transport measurements from both Xiaodong Chu's group and Ting-Xin Li's group, one from UW, the other is from Shanghai Jiaotong University. Directly observed the quantized RXY fractional values from transport measurements. And very soon after that, there is also the discovery of the FCI states in Longju's group at MIT on an layer from E moiré system. And there's also a work at Dan Feldman's from just the tungsten selenide, attempting to see the fractional Chern insulator. But I think probably the bands are not flat enough with this system. It depends on the detail. There's no FCI observed, but there is a Chern insulator observed in this system. So I'm not going to go through all of this. Let me just tell you our story of using thermodynamic measurement to drop the FCI states. A bit about our measurement scheme. This is our device structure. We have a sample here. The sample is between a top gate and a sensor. I'll tell you what it is. And then there's bottom gate. So you can think of it, the top gate and the sensor function as two independent gates that can tune the electric field and the filling factor of the sample. And the function of the bottom gate is to really fix the sensor to a set point. And that's actually used to read out the chemical potential of the sample here. So our sample is a twisted molybdenite here, and sensor is a monolayer of tungsten selenide. Both are TMD semiconductors. This is the sensor, and this is the band structure. And you can think that a natural reference point for a semiconductor is to actually move your Fermi energy to one of the band maximum or minimum, right? Either the conduction band minimum or the valence maximum. And the readout in our experiment is actually to look at the strength of this interband transition, the exciting electron from the valence band to the conduction band. And this is an example curve of the strength of this transition as a function of the bottom gate, which tunes the sensor Fermi level. And here you have very strong optical transition when the Fermi level is inside the gap. But once the back gate moves the Fermi level to cut through one of the bands, you can think of it now as just strong Pauli blocking of the optical transition, and you can see that the strength of the optical transition just dropped a lot. And this sharp transition here actually sort of gives us a sharp edge sensor, and that provides a reference point that we can log in our experiment. So in our experiment, what we do is that we use the top gate and sensor to independently tune doping and electric field. We use a bottom gate and a feedback circuit to actually fix the sensor at this particular point that the Fermi energy is always locked to here, which corresponds to this point in the readout. And if you can achieve that, you can solve the electrostatics of the problem that the chemical potential sample is given by the bias voltage that you apply between the sample and sensor, and the backgate voltage that you apply to keep the sensor at the reference point. And on top of that, you have the ratio of the capacitance, which you can calibrate very precisely. Okay, then you can read out the local chemical potential of the system with a spatial resolution about 1 micron. So this is a map of the incompressibility, the chemical potential over the filling factor, the nu. And as a function of electric field and filling factor, it starts to look something like a phase diagram I told you before. That is this region here, which is the small electric field region that the bands are topologically non-trivial. And if you apply large enough electric field, and I will show you later that the bands actually become topologically trivial. And so this is the region, and these are some line cuts of the incompressibility versus density, a different electric field. And all I want to point out is actually that this blue curve here, which is cut along zero electric field line here, you can see it in compressible states at filling factor 1, filling factor 2/3, 1/3, and 1/4. And you can also do magnetic circular dichroism for measurements on this type of material to sense whether there's time reversal symmetry breaking. And for instance, if you park a filling factor equal to 1, you scan the magnetic field, you see a clear magnetic hysteresis, and that the signals time reversal symmetry breaking. And if you do it at the 2/3 state, which is parking at here, and you can also see time reversal symmetry breaking from the magnetic hysteresis. So now what we have shown is actually that both the nuclear 1 state and nuclear 2/3 states are ferromagnetic, and they are insulators because they're incompressible. So I think the important question is just that whether these ferromagnetic states are trivial or non-trivial, whether they are Chern insulators, and if they are Chern insulator, are they fractional Chern insulators or not? And the way we do it is to use the Schroeder formula, which basically tells you that how the filling factor of this incompressible state dispersed with the magnetic field. And this is the filling factor, T and F some quantum numbers, I will tell you what it is. And phi is just the magnetic flux over the magnetic flux quantum phi naught. And T is basically the number of electrons added to the sample for added magnetic flux quantum due to topological pumping. And the S is the number of electrons added to the sample for added moiré unit cell to the sample. And if it's a topological trivial state, T has to be equal to 0 because there's no topological pumping. And so the state does not disperse with magnetic field. And if it's an integer Chern insulator, both T and S are integers. And if it's a fractional Chern insulator, T and S are commensurate fractions. And what that means is actually that if it's a fractional Chern insulator, if you add one magnetic flux quantum to the system, it adds a fractional charge to the sample. And it will just disperse, with a particular slope. So let's take a look at the data here. What I'm showing again is the incompressibility line, but now in the axis of filling factor and magnetic field. And in this plot here, we are keeping the system in the layer hybridized region that the bands are topological. You can see again, it's incompressible state at filling 1, filling 2/3, maybe also a very weak state at 3 bits as well. And for comparable, okay, actually I want to say that both of these states you can see a clear dispersion with magnetic field, and so it's a signature that they are Chern insulators indeed. And you can also tune your electric field now to make the system in the layer polarized region that the bands are topologically trivial. And in this case, you can actually see that the new 1 state just does not disperse with the magnetic field because this is just a non-topological insulator system. Okay, and I'm not going to get into the details. The nice thing, with the sensor here is actually that we can build the sensor to look at quantum oscillations, and that can actually help us to determine the capacitance of each of these gates very precisely. And then we can actually determine the moiré density and the twist angle of the sample very precisely. So that we can really use the Strader formula to determine quantum number T and S. So after all this calibration, what we can do is actually that so in this state, the 2/3 state, and we can actually determine T of about 2/3. And so the T and S are both 2/3. And for the new 1 state, both quantum numbers are 1. So one is an integer Chern insulator, the other is a fractional Chern insulator. And furthermore, it's just totally confirmed by direct for measurements that this is a fractionally quantized all systems. This is an integer quantized systems. And these states are actually quite robust against this angle. You can change the twist angle from 2.7 degree all the way to 3.8 degree, and you can actually just get the same results. The 2/3 states, 2/3, 2/3, splitting to the 1 states 1 and 1. So it's just over a range of this angle, you still get this FCI and CI states, and they are not quite sensitive to the angle. And finally, I also mentioned that you can use the electric field to introduce topological phase transition. In this case, you can apply electric field to make the bands topologically trivial. And this is the data for filling factor equal to 1. A small electric field is a Chern insulator, and this is plotting the chemical potential jump of the state, or you can think of it the energy gap of the state as a function of the electric field. And you can see that when you go from a Chern insulator to the Mach insulator, there is a gap minimum, suggesting that there's a gap closure in this topological phase transition. At the top here, what I'm plotting is actually the magnetic ordering temperature, the TC, the red dots, and the Curie-Weiss temperature are the black dots. And you can actually see that at the point of the topological phase transition, the TC actually drops to 0. And once you go into the Mach insulator, the Curie-Weiss temperature becomes slightly negative, suggesting that you have the antiferromagnetic interaction between the local moments. And that's for filling factor equal to 1 for the Chern insulator. And this is filling factor equal to 2/3, fractional Chern insulator. You can do the same exercise. This is the FCI, and the gap goes to 0 at the critical electric field. And it just suggests that the system actually goes to a compressible state, and it's possibly a Fermi liquid. And at the top is again showing the Curie-Weiss temperature as well as the ordering TC. The ordering TC is the red dot. At the point of the topological phase transition, the TC also drops to 0 and becomes negative in this Fermi liquid phase. And the negative Curie-Weiss temperature is not really meaning antiferromagnetic interaction. It's just the Fermi pressure of the Fermi liquid in this case. That's what we think. Okay, so that's it's sort of interesting that the system, you can just not only observe the state, but you can tune some knobs to also cause this interesting topological phase transitions. Yes.
Yeah, so I was curious. You found a 2/3 state, but no 1/3 state. Any thoughts on why that is?
But this 1/3 state. The 1/3 state is actually a trivial. It's probably a charge density rate. You can actually look at the dispersion of the magnetic field, and you just get a nearly 0 state.
Any idea why that one is not topological, the 2/3 one is?
There are some theories. I think the idea, if I'm correct, the idea is that the band here is not totally flat like a lambda level. So you don't really expect an electron hole symmetry except if filling factor equal to 1/2.
Thank you.
Yeah.
I also have a question. So if I look at this plot at large displacement field, I think I see like a d mu d nu step at 2/3. Yeah, is that signal?
Actually, this is zero electric field. It should be plotted a little.
Oh, okay.
Because the structure is not, the structure, if you have a sensor on one layer, the structure is actually not really making the true zero field at really zero. So it's not shifted, but this is a real zero electric field.
Okay, so the blue curve on the right is real zero,
electric.
and the red is finite.
Yeah.
Okay.
The nominal zero is actually not zero. It's high electric field.
Thank you.
Okay, so I hope that this is the first part. I hope that I convinced you that there is a fractional Chern insulator in this system. And now we just move on second part of trying to convince you that we have observed a time versus symmetric PI states in this system. Very quick introduction to the spin-off needed. It was first pointed out by Kane Malay in the 2005 Kane Malay model, and very soon after that, Hughes and John proposed a model for mercury telluride, and that actually the experimental valid model very soon after that realized experiments. And maybe the simplest way to understand the quantum spin-off effect is that you have just the Haldane model, and you can just think of it that it's two time reversal copies of the Haldane model in the limit that the Kane-Malay model has no large spin-off interaction. And so it's two time reversal copies of that, and next nearest neighbor hopping in this case would be a time reversal symmetric spin-off interaction. And so because you have two copies instead of a quantum anomalous Hall insulator with a chiral edge state, here you actually have two copies of chiral edge state, counterpropagating edge state that are spin polarized. So we call it the helical edge states. And experimentally, you would expect you to measure zero charge Hall effect for the quantized spin Hall conductivity. This nobody knows how to measure quantized spin Hall conductivity at this. For fractional TIs, basically at this point you can think of it any quantized version of Hall effect can be fractionalized. So fractional TIs is TIs with fractional electrons in the bulk. The stability of the edge state is a subtle issue here. Actually, the fractional TI was first pointed out in this paper by Benedict and John, 2006, and later on really further developed by Levin and Stern in this 2009 PR. These are the two review papers we're interested in. These two review papers, and maybe the simplest example of a fractional TI is time reversal copies of FCIs. So now we have an FCI system. Maybe in the right range of parameters, you can actually hook up two time reversal copies of that, and you could realize a fractional TI. So experiment on 2D TIs first discovered in mercury telluride quantum wells 2007, and later on in monolayer tungsten telluride 2017, and also recently in moiré semiconductors. I highlighted an example already, but the fractional TI has not been realized so far. And this is our recent preprint, and we look at a 2.1 degree twist angle device, still twisted moiré telluride. And compared to the earlier studies, which focus on for devices between 3.5 degree and 4 degree, this is about half of the twist angle. So if you convert into moiré density, that's really 1/4 of the moiré density. So we are dealing with much smaller moiré density in this system. And this is our device structure for the experimentalists who are interested in. This case, this is the twisted moiré telluride, and we have a monolayer of tungsten selenide to form a tunnel barrier between the platinum context and our sample. And the sample is gated between top gate and bottom gate here. Okay. And on top of the top gate, we further define contact gates to heavily dope our twisted moiré telluride directly in contact with the platinum to form a good electrical context. And then we also have the split gates. Basically, we just turn off those regions that form a parallel channel, so that we just make sure that there's no other parallel channel that's contributing to the transport of device. This is the device structure, and we only actually have these 4 contacts in this region that have a nice moiré system. So I will be focusing on this region here that's contacted by 4 electrodes. This is the channel here. A few more words about the contact for the experimentalists. We heavily hold the twisted MOT2 region in direct contact with platinum, so that we can actually reduce the contact resistance a lot. And you can sort of use this resistor in series circuit to understand the contact. And as far as we understand, the contact resistance is dominated by the junction between the platinum and the heavily doped MOTE2. And the heavily doped MOTE2 to the channel, actually the contact resistance is negligible. As I will show you that this contact here is very transparent. And this channel here is gated by the top and bottom gates, so that the contact resistance is nearly independent of the electric field and the doping density in our channel, because the channel just never affects the doping density of the plate that's directly in contact with the metal. So that actually is a pretty important aspect of our device that allows us to subtract the contact resistance in the next slide. This is the contact resistance as a function of temperature. It has a pretty weak temperature depending on the milli-Kelvin temperature. So we believe that we have pretty good contacts tunneling contact regime. And the contact resistance per contact is about 20 to 25 kilo ohm, depending on how much we want to push our contact gates. We can push below 20 kilo ohm also. But 20 kilo ohm contact resistance doesn't sound very impressive if you're working with plug-in devices, which is about probably 1 to 2 kilo ohm. But if you do a TMD, it's pretty good. Oh, and another word about twist angle, we calibrate using the Landau band of the sample, so that we keep the twist angle calibrated is also correct. You're interested in this first, right? So the first measurement that we do is actually we bias the current along this diagonal direction and measure the voltage in the other diagonal direction. So this is a 4-point measurement. And this is the longitudinal resistance map as function of electric field and filling. This is the Hall resistance map. And you can now see actually there are states at filling 1, filling 2, filling 3, filling 4, 6, and 8. So compared to the large twist angle device, typically they can only see insulating states up to filling factor 2. Here, we actually can see filling states up to filling factor. We actually can scan further. We can actually observe states beyond filling factor 10. So it highlights, at this very small twist angle sample, you actually, the bands are really, really flat and you get lots of correlated states, or maybe not all of them are correlated. So you just get states, insulating states. And this is a Hall map. Maybe actually the clearest, data to show is to just cut a line cut at the zero electric field. And I'm plotting the blue curve is the longitudinal resistance, and the red curve is the Hall resistance. And you can actually see that the filling factor to 1 is a quantum anomalous Hall state. It's very well quantized over E squared with the vanishing longitudinal resistance. And that's just expected. Maybe there is FCI state here around filling factor either 4/3 or 3/2. We are not very sure about that. But at the integer fillings of filling 3, 2, 3, 4, and 6, you can actually see quite strange behavior that the longitudinal resistance nearly vanished at these integer fillings. At the same time, the Hall resistance also vanished at these integer filling factors. So I'll come back to that, how to understand these states. Because these states actually do not throw off anomalous Hall response, they cannot be translated, so they are not chiral. But at the same time, they have a vanishing longitudinal resistance, so that requires some explanation. I'll come back to it.
Fine, on the last slide, I remember reading the state at 4. It looks like you're not really reaching 0 with the RXY. It's like
Yeah, it's
is that worth remarking on, or is that just within the margins of error?
I think it's not really, we can measure it quite well. Yeah, it's a small value, but not exactly.
All right, thank you.
Yeah, so you said that your SZ is concerned, right?
SZ is concerned.
So if you're sitting at 2, can you open the measurements to see if the.
We have done both out of plane view, in plane view, and the quantum speed is sensitive only to in plane.
Right.
Yes. And that's consistent with SZ constant. And in fact, if you actually go to the bulk states, it has no in plane view dependence, which is it. So to understand this state, these states better, we actually perform a 2-terminal transport measurement here. And this is the measurement circuit. Sorry, it's a bit small. What we do here is we actually short these two contacts here and short these two contacts here and just directly measure the terminal resistance in this way. And this is the result. blue curve is the two-terminal resistance after a subtraction of a constant contact resistance. And how we calibrate the contact resistance actually built the system a lot to filling factor beyond 10. And then we just calibrate the two-terminal resistance to the four-terminal resistance. At that point, the four-terminal resistance is only 100 to 200 ohm. So we just calibrate to that point here and subtract one constant, and automatically you get the filling factor 1 equal to h over e squared. So that's expected. And at the same time, you also get this h over 2 e squared, nearly h over 3 e squared, 4 e squared, 6 e squared plateaus. And the bottom is basically plotting 1 over the two-terminal resistance. You can, this two-terminal resistance, you can see 1, 2, 3, 4, and 6 those steps in this device. And the red curve, we're just comparing the Hall resistance again, zero Hall resistance at 2, 3, 4, and 6. All right. And so what do these data mean? First, the nuclear pump is a Chern insulator, so you get a two-terminal complex conductance to h over e squared. And the states at 2, 3, 4, 6 cannot be chiral states because you have vanishing Hall response. And we have something that is a quantized two-terminal resistance, but with vanishing Hall response, the best we can think of is quantum spin Hall insulators. And at u equal to 3, in this particular geometry that involves two edge states, it actually means that each edge supports a quantized conductance of 3½ quantized conductance per edge. So it's most likely a fractional quantum spin Hall insulator. We can do a little bit better. We can perform a non-local two-terminal resistance at varying measurement geometries. This is the geometry that I have shown to you. And you can actually use a Landau-Kutiger formalism to calculate the effective circuit diagram for these states with the two edges here. And this is actually a resistance for one edge here. This is a resistance for another edge. So this is a resistor in parallel. And then you can do another geometry, which is to flow one of the contacts here. Because we are dealing with helical edge states can actually equilibrate potential at each of this contact. So what effectively this contact does is to cut through one edge state and split into two resistors. So what the effective circuit of this is that we have one resistor here and two resistors in series here. So it's 1 and 2 in parallel. And you can do the same exercise again for this circuit and that circuit. And this circuit in particular, you have two edges on each side. So it's two resistors in series and then in parallel. So this circuit is effectively measuring the the resistance per edge. So this is filling factor equal to two-terminal conductance scan versus electric field. And for this circuit here, you get actually e squared over h because you have two edges in parallel. For this circuit, you get an effective 1 e squared over h because you effectively measure one edge. And for these two is somewhere in between. And the dashed lines are the expected values from Landau-Kutiger analysis. So the results agree reasonably well with this scaling of the resistance with changing configurations. This is filling factor equal to 4 is a weaker state with a smaller gap. It's sort of reasonable. You still get similar results, except that in this case, the blue curve takes 4 e squared over h, the red curve takes 2 e squared over h. So each edge actually contributes to 2g0 per edge. It's the double quantum spin Hall insulator. And the most interesting state is the nuclear 3. That the blue curve takes 3 e squared over h, the red curve takes 3½ e squared over h, 3½ e squared over h. So it means that it takes actually 3½ of conductance quantum per edge. Again, it just confirms that it's most likely a fractional quantum spin Hall insulator. Okay. A few comments about this state. So we observe states at 2, 4, 6. They are single, double, triple quantum spin Hall insulators. And so it suggests basically the Chern number sequence of this device that we have takes +1, +1, +1 in the k value and -1, -1, -1 in the k prime value in this system. So that it supports the single, double, and triple quantum spin Hall insulators, these filling factors. And I want to comment that more than one pair of helical edge states allowed in this system because it's not really protected by Z2. It's actually protected by SZ conservation. And as a result, an even number of helical edge states is okay is allowed in this system. And for the equal to 3 fractional PI, is corresponding to a half field level that with the Fermi energy located, in the middle of the lens here. We suspect that most likely it's 2 time reversal copies of 3 half FCIs, and because it's half filling, the composite fermions will still a zero magnetic field, and since it's a gap state, we probably the experimental data maybe suggesting the composite fermion pairing for these states.
Sorry, I just have to, but you say as Z is conserved,
Yeah.
but how good a conservation? Presumably, that's not exact, there isn't a symmetry.
Yeah, and so the spin orbit field for the
Yeah.
valence band for monolayer material is 200 millivolts,
Uh-huh.
and the bandwidth of all these flat bands will normally be 10 millivolts,
Uh-huh.
something like that. And so you basically that this is like this is all from one spin band.
Yeah.
The other spin bands are down here.
Uh-huh.
So I think the spin orbit field is like 1,000 Tesla or something. The Ising spin orbit field.
Uh-huh.
So it's I think in terms of the energy scale, this is a very good approximation.
No, but I think what you worry, I guess, is something scattering from one balance to the other and flipping spin,
Yes.
which is allowed.
Yes.
I mean, not by momentum conservation, but.
Yeah.
Disorder.
And I think that may be so that actually takes an atomic scale defect
Yeah.
to do it, and I think that may be one of the reasons that our devices are quite good is that our edges are electrostatically defined,
Uh-huh.
so it's a pretty smooth potential
Uh-huh.
on the edge, and it's not really like a physically terminated edge. There's lots of dangling bonds.
Uh-huh.
So that may be the reason that this is pretty well quantized. Yeah, this quantum spin by insulators.
Uh-huh.
But maybe at nu equals 4, so the gap scale is smaller, it doesn't look.
Yeah, the nuclear fault for some reason is the least well quantized that we have. So maybe it really has a little bit of a number of pair that is a little bit less robust. Yeah.
So can you go back to the diagrams? So here, does the contact resistance come in, or is it I guess here the other leads are floating? But yeah, that's
So yeah, we again do this a calibration of scanning to a very high density and subtract the contact resistance for each configuration with the bottom.
but for the resistance, does the contact resistance play a role or not?
In these two terminal measurements, yeah, it raises a background.
But I'm sorry, I mean, between the when you show the resistor diagrams,
Yeah.
Going from one end to equilibrate, you have another stretch
Yeah.
edge to equilibrate.
Yeah.
And there, suppose you make.
Yeah, and that's why we think can think of it like this. Since we just subtract one constant and measure a pretty good at a quantum anomalous state, pretty well quantized over E squared. That means actually that in our contact, going back to here, the heavily doped region to the channel, this contact is quite transparent. Otherwise, you cannot really get value that's pretty close to H over E squared.
So you're saying that the
contact resistance here is negligible.
so if you go to the resistor diagram, the contact resistance, at the left and right, it's not negligible, but within this structure.
It is different, yeah, to the matrix. Yeah, it's a different kind of contact. Yes, exactly. Here is really from the channel to the heavily doped region, and we believe the contact there is very transparent to us. We cannot get that. Yeah, I should wrap up quickly. Now we can actually come back to the 4-terminal resistance again. Now it's sort of explain why, for all these 2, 3, 4, 6 states, we have nearly vanishing both Rx and Rxy. The reason is that these states are quantum spin Hall insulators, so that the effective circuit here is basically like a resistor bridge circuit for the edge states. And so we get nearly vanishing Hall response and also the longitudinal response for these states. So it's consistent with the quantum spin Hall insulator also. Finally, the energy scale of these states, you can just form it up and see when plateau vanish. And for the nuclear state, it's actually very robust. It survives about 12K. And for the nuclear 3, it disappears between 3 to 4 Kelvin. So it's this gap size is a relatively small gap. And you can also look at topological phase transition driven by the electric field. I think I'll just skip for the interest of time. So this is a summary slide. I don't want to read things again, and I think it's quite exciting that we find the quantum spin Hall insulator. Can we find other quantum spin Hall insulators, and can we make some interesting devices, fractional charges and things like that? Interesting question to ask. This, thank you for your attention.
We've already had some questions, but they're more, yeah.
Yeah, thank you, really interesting. So do you have any remarks on whether or not time reversal symmetry is also present in addition to the SC conservation? So you've answered so far that's the SC conservation, but the question is, does it also have time reversal symmetry on top of the SC conservation?
Yes.
It's always something.
Yeah, the
SC conservation can also do that.
Yeah, as far as we can tell, is that the Hall response vanish here. So we think it's a time reversal symmetry state.
Okay.
Yeah. The time reversal symmetry breaking is actually, in fact, actually, once you dope a little bit away from it, the system immediately breaks time reversal symmetry. And all these Hall response are actually anomalous Hall response. You can scan it. It's basically like it's ferromagnetic.
And so this is always taking in the same direction.
If there's some additional data for like this, for instance, in particular 3, you have nearly vanishing Hall response. This scale is actually pretty small, right?
Actually, you probably said this, but RXY is an odd component. It's RXY minus RYX, or could it just be?
So what we measure is that we measure the transverse voltage under positive, under a small positive magnetic field with anti-symmetric respectively.
Yeah.
It's an anti-symmetric component.
Yeah.
And yeah, you can see that slightly below filling 3, you get a nearly like a ferromagnetic response. I'm not so sure it's really exactly ordered and maintained a zero field Hall response because we did not really scan that fine in these scans. But above filling factor 3, you can also see that it's actually nearly a ferromagnetic.
So this is for field along Z.
Yeah.
You have data for the in-plane. Well,
Yeah, in-plane is actually something. Oh.
no.
Yeah.
And so just one very quick one.
Oh, it's not here. Yeah.
Yeah, so is there hysteresis in those magnetic field sweeps? I couldn't tell in the paper.
Well, the coercive field is going to be very small. We have not scanned the finding enough to show that, yeah, it is.
Thanks.
Maybe I missed it, but in the two terminal conductance, well, have you excluded have you excluded the possibility of additional trivial edge states? Like you could have like a one-dimensional channel on the edge, which gives you a twist over edge.
Yeah, if you have this, then for some, I guess this is always an issue for this kind of measurement for quantum spin Hall that I think in principle, unless you really measure the quantized spin Hall conductance, in principle, in this kind of resistance measurement, you can never rule out the possibility that you have a gap Hall and a nearly ballistic edge states that can equilibrate with but you still get the same scale.
Well, but like for example, the simple quantum spin-Hall case, the argument is that you will have like one spiral rate on the edge, which is not possible for the trivial state. But the other kind of configurations, then there is a possibility that there is an edge state this way, but not that way. So just there is more possibility to exclude. So I'm just wondering if that has been, like in the case of 3, I don't know, naively, I don't see any way it would come from additional edge state, but there's something needs to be excluded.
Yeah, it's fine.
So I'm a cold atom experimentalist, so I have what I think is maybe a somewhat naive question. What? I think I'm quite naive.
I just said you're warm, you're not cold.
Quite warm.
You don't, but actually, our atoms are warm compared to cold atoms. You went to call me a lukewarm atom experiment.
That's not all I like.
And we're friends. Think about that. The question is, can I even remember what I was gonna ask? Absolute disaster, right? So my question, which I'm quite confident is naive, is you made this comment that it's hard to measure spin Hall conductivity. Why is that? Is it because it's hard to measure spin conductivity? How should I?
We don't have a spin wire.
You don't have a spin sensor or a spin wire?
You can have a spin sensor. You can measure spin accumulation. That you can actually measure the presence of the spin Hall effect pretty well. But to quantify that value, it is not.
Could you measure it in a non-equilibrium setting before the spins have accumulated? Like
can
the
measure the
rate
spin
of
accumulation.
accumulation?
But that accumulation depends not only on the spin Hall conductivity, but also on the scattering times. Scattering times of the charge area as well as the.
That's the amount of accumulation,
Yeah.
right? But if you measure the rate of it going before it starts to equilibrate, wouldn't that
Yes,
give you?
yeah, I think if you can measure the time dependence of that, yes,
So what's the time scale then?
So it's a geometric mean of the scattering time and the spin lifetime. The spin lifetime is not very well known. Yeah, not really measured spin lifetime.
There is, probably it's not relevant, but there is a fundamental problem, which is spin isn't really certain.
Yes, you have magnetic impurities, they get that scattered shift.
Well, just, you can't have wires that have a conserved spin current, you have a charge current, but.
Maybe you can, design a clever channel device that, you drive a spin Hall effect here and measure the inverse spin Hall effect very far away. If your edge state is really coherent and can over a long length scale, then you can possibly back out the spin Hall conductivity. Yes.
Thank you.
Are there more questions?
Yeah, so thanks for the beautiful talk. Looking at the data, what strikes me most is that the need is 3, the geometry where you have the right hand geometry corners, which is the one that is the each squared over h? That's the
It's 3D.
right. So yes. So that one seems to be both remarkably well quantized by the standards of started off with the statement of part pavilion, and now you're at quantum spin Hall, and quantum spin Hall has never been well quantized. Let's say to a year ago or and so I find it quite remarkable how flat that plateau is and how close to the quantized value. And do you have any speculation about why that's more true for that? That's well, that theory and maybe
I sort of believe that the good quantization actually new with the test. I mean, it's really well quantized here, and it has a larger scale. And I sort of believe that the good quantization, quantum spin Hall is because of that state conservation. So that it's really quite well protected from backscattering compared to Z2.
So but going back to the plots that you were showing at the beginning, I think there's a new constellations for that geometry. Maybe that's crazy, but it's much better than you expect. There's this plateau that is.
Oh, I think it's probably just, I think that Newton 3 is generally not as good as the Newton 2, maybe just. Yeah, for this specific curve over here, that was, I think it's somewhat accidental, yes. Yeah, it's less good compared to that.
Are there questions?
I have one more, or is that